Wave, how it works and how you get into it. And then tonight we'll talk about what you do once you've got into it and how you move around in it. A lot of people here who regularly fly in waves, so we should have some good discussion points. However, the first thing, how does the wave wave? Why does it wave? Back to the concept of making models that we can use to discuss the physical world. You've heard about Newtonian physics, Einsteinian physics, and quantum mechanics. All completely different models. Yeah, if you want to play baseball, then Newtonian physics is great for baseball and billiards and putting a table together. If you want to design a fusion bomb or a fusion reactor, then you need quantum mechanics. And if you want to send a spacecraft to orbit Jupiter and Saturn and send pictures back, then you need Einsteinian mechanics. And of course, GPS, for instance, if you don't take any notice of Einstein, you can't build a GPS system. The clocks in the satellites run at a different speed to the clocks on the ground. Crazy, but there you go. So, models of wave. The simplest way to understand it is to use a model that discusses the temperature profile of the air mass, and we talked about that yesterday. One of the things that, flying in New Zealand, I've had the joy of flying, lots of wave flying, obviously. Flying with smoke in the convective layer, so you can see the convective layer very clearly underneath you. Flying with smoke in the wave layer, so you can see the wave trains very distinctly. And flying in blue wave, of course, it's been entertaining. That's kind of enabled me to build up a picture of the mechanics. But one of the things that really I found very curious for years, when the wind isn't very strong, you still find that the positions of thermals are governed, quite often they're governed by the wave, even when the wind isn't very strong. When you have a temperature profile which is set up to drive wave, you'll get wave influences on the thermals, even though when you get into the wave, it's really weak and floppy and not really much use at all. But it'll still strongly position the thermals. The effect of wave on thermals is because of the amplitude of the wave and the amplitude of the air movements, the depth of the wave, rather than because of the speed of the flow and the mechanical effect of tilted flow. It's more to do with the amplitude of the wave, the lifting, the sinking, and the effect that that has on the local tephigram. So let's talk about wave generation. I'm going to draw 3 hill profiles. Let's get the right pens. I need a green pen. Day 1, deep convective layer. So a little bit of wind, flow, the air is not stable, it's neutrally stable. When the air is lifted up to here, it has no tendency to return back to its original level. It's a thoroughly mixed layer, right? So there's no tendency for it to return to its level. It's not wanting to come down the back of the hill. Why would it? Once it's lifted up to here, it's happy to be here. And Thermals forming cumulus. So a thermal rising from here, rising up the face of the hill, will come up here, and you'll get cumulus coming off the mountain. And that's one type of weather situation, which is very nice. Wouldn't we like to have that? Okay, next type of weather situation. Let's bring the inversion down a bit. And we'll have the inversion a bit above the hill. Not low on the hill, you know, well up, maybe half the height of the hill, sorry, twice the height of the hill, 3 times the height of the hill. The air that's lifted up here, coming from up here, is lifted in that area and does have a tendency to return down. We'll come back to this tendency. We'll come back to the spring effect in a moment. A little bit more tendency for the air to flow over the ridge and down the other side. Thermals can still come up here, and you might have thermals over the top of the hill. But as you bring the inversion down, there's more of a tendency for this to come down the other side, and more of a tendency for the thermals to wash out on the back of the hill, and more of a tendency for the air to generally rise up over the hill, and for the wind to rise up over the thermal layer and come down on the other side. If you have an inversion and wave on the top of it, and there's plenty of room for the hill to operate, then you might well have this situation where you have a band of thermals on top of the hill and the wave on top of it. And we'll come back to this because I want to look at the extreme example at the far end, which is more your conventional wave soaring situation, which is where you have a pretty solid inversion, pretty low down, and that really changes the nature of the flow. Situation number 3, pretty solid inversion, pretty low down. So let's put the inversion about here, a bit above the top of the hill. What you'll see is a cloud, if you have a cloudscape, like this, and what's happening with the flow, because of this inversion here, we talked about the air from here not being able to get up much higher because of the temperature inversion. So the flow looks like this, and that blocking effect just lifts the flow up a little bit ahead of the hill. And you have wave on top and the wind comes down the back of the hill. And this is a classic wave soaring situation with a lowish inversion, the hill out of phase with the wave, what we call out of phase, the thermals being in front of the hill and the wave being accessible somewhere here. As you lower the inversion for a constant wind speed, let's say 15 knots, you go from a mountain soaring situation with thermals coming up and making thermals drifting off downwind to a situation where the thermals come up in front of the hill, not off the top of it. And somewhere in the middle, you'll get an oscillation over the top of the hill. And that's really a question of the depth of the convective layer. We had this in Denby last week. We had one day when the thermal arc of the thermals and the arc of the wave was smack on top of the hill. It was quite a deep convective layer. Let's talk about the mechanism of driving the wave itself, and then we'll come back to this generator. I'm getting warm now as it warms up, so I'm going to have to take the top off and redo the mic. See that? Okay, so we talked yesterday about stability, and we talked about the fact that if you take a parcel of air from here and you lift it, it expands, and suddenly it's colder than the air around it. Colder, use of color, G. Restoring force, because it's colder. There's a restoring force. It's colder than the air around it, and it wants to come back down. It's colder, so it's not buoyant. And if you lower the air, compress it, it's warmer than the air around it, and so it wants to come back up. This is what drives the wave. So forget the mixing layer for now, and just imagine the streamlines. Imagine it's 6 o'clock in the morning and there is no mixing layer because it hasn't started to get sunny. So here's a streamline running up against a hill. The hill gets in the way, it pushes the wind up. So here's the hill, here's the wind coming from here, it pushes the wind up, it comes to here. Temperature profile here, temperature profile is different over the hill. This is going to reduce its temperature at 3 degrees 1,000 feet. And it's colder than the air which is off to the side. We'll draw a sounding for this time of day. Lift this air mass, boom. It's colder than the air around it, colder than the air off the hill. So there is immediately a restoring force that brings this back down. It's heavy, so it comes back down the back of the hill. In wave soaring conditions, when a hill's acting as a wave generator, the wind is blowing down the back of the hill. It's coming down the hill like that. And this is not a good place to be flying because you've got off the clock sink here. It comes down the hill and it keeps coming down. Now, it doesn't come down the hill and get to its rightful place and then blow along level. Remember, a thermal was 80,000 tons of air, cylinder of air, half a mile deep and a quarter of a mile across is 80,000 tons. Imagine the mass of a cylinder, mass of air blown over Benati or the Bishop. Imagine the mass of that, say the bottom 5,000 feet by the width. I mean, it's billions of tons of air coming down the back slope. So it just carries on down. The momentum, it has momentum. As it comes down, it heats. And it is now warmer than the undisturbed flow. And that heating and buoyancy turn the direction of flow back up again. So this air mass lifts and cools, springs back down again, overshoots its mark, comes down here, heats, turns around, goes back up again, overshoots its mark. Now, discussing wave flow in terms of temperature is kind of important because what controls thermals? Temperature of the air around them. So restoring force, and that's what drives the wave. That's what happens. The restoring force depends on the amplitude of the flow and the temperature profile. The speed of the flow governs this, to some extent, governs this momentum, but not entirely, because part of the momentum is just pure vertical movement. Anyway, there you have a wave system. Now, we don't have a mixing layer in this wave system. And of course, this air is stable air. A package of air flowing along here isn't going to carry on flying along here. It's going to go up over the top. And up over the top and up. So then you get the vertical propagation of the MS. These layers don't want to mix, so they just tilt and flow up and down and up and down and up and down together. So far, so good. That's what drives the initial spring in the wave. Or that's a model which is useful to describe the initial spring in the wave. So let's go back to drawing our wave trigger. And let's draw a few clouds. There's your mixing layer. The clouds show you where the thermals are going to. It's much easier with cumulus at the top of the mixing layer. The top of the thermals define the bottom of the laminar layer. So straight away, you can see where the wave arc is. Yeah? You can quite often, when you're flying in thermal conditions in wave, with wave on the top, you can quite often look to the side and you'll see a whole bunch of clouds rising up and falling down. You go, oh yeah, that's underneath the wave. Those of you that are experienced in flying thermal to wave will recognize that shape. That's where the wave arc is. So you can predict, join the dots, somewhere there's going to be but you don't see the green line. You're only going to see that. And we call these rotothermals. And you might see above it, if it's a nice day for making clouds, you might see some sort of lenticular over the top. Might be pointy, doesn't really matter. So you can infer the process of wave from looking at the lenticulars, but let's just forget that for now. Whether there's lenticulars or not depends on whether there's wave there, but it also depends on the moisture level there, because if lifting doesn't cause condensation, you won't have a lenticular. Think about what's happening with the flow. I'm going to draw the wind here, windy. I'm going to draw the wind here. Not very windy. Draw the wind here. Windy. Sorry. Distracted by use of color again. I was thinking I hadn't done it in red. Not very windy. Somebody should have gone, gee, that's the quiet bit. What's happening here? The flow is moderate here. It's getting blocked by this hill. So the wind speed reduces. Here the flow compresses and is windy on top of the hill. The air comes down the back of the hill and comes down here. The flow is thin. It's thin here, but also because the wave is coming down here, all this air mass that was flowing from here has got to squeeze through here. And it's also got to squeeze through here. So here's windy. It's quite possibly not quite as windy as it is on the summit of the hill, but it's bloody windy here. One of the characteristics of standing on the ground, you know, walk around in a banging wave system, and you can stand here and there's no wind at all, and you can hear the trees breaking a couple of miles away. You stand here and you can hear it howling here, and you can hear it howling a distance away because it's quiet where you are, which is unusual on a windy day. You can't normally hear the wind howling through the trees 2 miles away because it's howling through the trees where you are. But in a wave system, as the wave arc goes up, the wind falls light on the ground. That's just a Bernoulli thing. There's not enough, because the wind's not, the lower level wind isn't getting through this line. It's not going to get through this line. So it has to go through here. So it has to speed up. And then as it expands here, then the wind falls light. The lower streamlines will go up and down to some extent. So you've got a wind here, falling light. The lower streamline falling light, speeding up, speeding up, speeding up, coming down here fast, then coming up, reducing in speed. Remember I said back when I was doing my thermal on the ground thing, the thermal takes off preferentially where there's less wind. Kate asked me about wind shadows. Underneath the wave, where the wave rises up, is effectively, it's like a wind shadow because the wind falls light on the ground. There's not a blocking thing there. It's just that the air mass has become deeper, the convective layers become deeper, and the same wind going through the bigger volume just reduces. So this is a great place to find thermals. This is also quite a good place to find thermals as the wind reduces in front of this blocking ridge. So generally in this situation, you would expect thermals to be coming up from here, but actually thermals are more likely to come up and form these clouds a bit in front of the ridge where the wind is reducing. The ridge is out of phase with the wave. Well, actually, this ridge is generating wave, and because the inversion is low, the top of the ridge is not really working very well, and thermals can't go up here properly. But where the wind is reduced and the ridge is blocking it, then the thermals can go up quite nicely, thank you.
I mean, chaps here often spend hours sitting on the ridge and pushing forward, you know. And the thing I always say is there's no point pushing forward unless you've got something to push forward to.
Yeah, you climb as high as you can around here, and you push forward, and you push forward, and you push forward, and hopefully you're going to get to cloud base around here. But if this is the wave generator, it is going to be hard to climb in proper wave here, because this isn't proper wave. This is just humping up over the hill. The proper wave is downwind of this hill. Because of this flow type, this type of flow that tends to be prevalent on wave days, if you're operating out of Port Moat, you're flying off Bishop, and it's banging wave up in the hills, up forward of you, you look at the wave and you go, oh, I'm out of sequence with the wave here. Well, you may or may not be out of sequence, out of phase with the hill being where the wave is already. But there will be a tendency on a lot of days for the flow to set up like this anyway, just to set up like this anyway. So it's going to feel like it's out of phase more than half the time. That's the thing, it's not just random. If you've got a good wave day, normally it's going to feel like it's out of phase with the wave. Sometimes the wave will move and the flow happens to be going up over the hill and it's just great. All right.
Can I just check?
Please.
In my experience, and it's not as great as others, is that on the days where you are getting into wave off the Bishop, you're not over the top of the Bishop. I know you can be, but most often times I've got wave over the lock, well forward of the ridge, and that's how I said to myself, it's waving because clearly at 2,500 feet, well forward over the lock, I'm not in ridge lift.
Is that wave not coming from the uphills or something?
Yes, it will be. It will be. Yes,
maybe.
Yes,
maybe it could be.
Yeah, you won't be soaring in wave off this trigger if there's wind from over there, and it's waving off here.
Yeah.
The wave from here is back here. You'll be going forwards to a system that's here, but locally the flow would look like this.
Yes.
That's the point.
The thing I always, I usually work on the principle that it takes 2 hours to get into the wave unless you're really lucky. I did a flight a few months ago when, which I cocked up because I got airborne onto the ridge, got straight into the wave, and then realised I'd forgotten to switch my oxygen on, and then landed, and then switched my oxygen on, took off again, and then it took about an hour and a half. But the point I was going to make is that, talking about normal days when it's not blue or anything like that, you've got to have an indicator, and it is a matter of sitting on the ridge and watching what the clouds are doing. And you can, you get, just to go a little bit further, you get times when the ridges increases and decreases. But the important thing is to see what's going on ahead of you, to see what clouds are forming, and they can be cumulus or scraggy cumulus, but I don't personally feel there's any point pushing out until you've got actually something to look at, or something, it takes a bit of time to get your eye in, to actually suss out what's going on with the day. I mean, to cut a long story short, I can't be asked with that. I take an aero tow, and go straight up into it. But that's not everybody's opinion. Is there any comments on that at all? Because on the ridge and all the rest of it, right? Does anybody want to add to that?
When the wind's veering significantly with height at that lower level, it's a hell of a lot easier to contact the wave in a ridge than it is if it's not veering. I don't know, is that just, chance on my part, or is there something behind that?
That's not making any sense to me. I'd need to think about that.
Yeah.
I hear what you say, and I understand what you're saying, but it doesn't make sense
No logic
necessarily, but there's probably something in there.
Can you say sense it?
Yeah.
This happens to me all the time, but I'm sitting on, oh, sorry. I'm sitting on the ridge, and as you say, there's nothing to see to push forward to, and the ridge is working, we're just sitting there and spend half an hour there and I'm getting bored. And then all of a sudden you just think, oh,
Bang.
we're climbing, and
Yes.
I haven't done anything.
Do you ever sing in the bathroom? When you're sitting in the bath, do you ever sing? Because the bathroom's a really nice acoustic space. And if you hit the right note, it will really resonate. So you can, and then you hit the right note and it all comes alive. I'm a musician, I sing in the bathroom. Wave is a resonance phenomena. If the wave, if the thermals and the wave and the shape of the train all happen to be in phase with each other, then you get a wave system. It's sort of going, and underneath it's a mess, and it's a mess, and it suddenly goes, ta-da! And you climb in, and then it goes, and it does that. It just comes into focus. It comes into focus and resonance, and sets up just now, just right, and then it goes away again. I'm going to talk about rotothermals, and you'll see why that happens. So I've drawn a better diagram, I guess. So this is the bishop, and this is the high terrain upwind, right? And you might be looking at this, looking at it from the side. The wind's left to right. So where you're going to get in, if you're climbing in rotothermals, I mean, if you can aero tow up to here, then all well and good, right? If you're stuck underneath it, or if you have been flying in a wave and you fall out of it and you want to get in and get home, then you have to understand how the convection is working under the wave. And if you're going to fly around here in thermals with any westerly, northwesterly wind over the top, there's going to be oscillation over the top that may or may not be useful wave, but it will help control the thermal. So what's happening? You need to understand the thermal layer. One way of understanding what's going on is to think of the depth of the thermal layer and the wind. Remember, the thermal layer goes to the top of the clouds. It's the top of the clouds which dictate the thermal layer. So this is here you've got, I don't know, a 3,000 foot cloud base with cloud tops at nearly 4,000 feet. So you've got a 4,000 feet deep thermal layer with clouds in it and maybe 8 to 12 knots on the ground. Here you have blue conditions, 15 to 18 knots on the ground, and blue thermals going up to maybe 2,800 feet. Which is going to be the best place to soar? Fairly obviously, the day with cumulus and less wind, because this is one day and this is another day. Think about the local T-phi. What's happening here? The air mass has been lifted. As it lifts, it cools. The whole lot cools. So if you started with a T-phi gram that looked like this, here it's going to be a little bit cooler. and the thermals will go a little bit higher. And here, if you started with the T-phogram that looked like that, here, where the air is brought down, it's going to be more like this, and the thermals won't go so high. It's a different day, different temperature profile. Locally, a different temperature profile.
Indeed, a different buoyancy shear ratio underneath one of them.
A worse buoyancy shear weight ratio because there's more wind and less instability. This depth of convective layer varying, this is what positions the thermals even when this wind is not strong, because it still goes up and down and it still positions the thermals. So that's a bit of a clue. So I first realized this myself. This was a way of thinking about it, the depth of the convective layer. I was flying in Marima, and I was flying to the south, and I was flying in the Dunstan Valley, and there was a lot of smoke in the convective layer, a lot of Australian bushfire smoke. And you had this situation, and you could clearly see, looking down from the wave, you could clearly see the convective layer getting thicker and thicker and thicker and thicker and thicker, more and more smoke, and then thinner and thinner and thinner and bluing out, and then really thin, lots of wind on the ground, and really thin convective layer, and then thicker, 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 thicker. You could just see it as clear as day. You've looked down on the convective layer. Well, if the convective layer is full of smoke, you can see it.
Just curious, what was the amplitude of that wave?
Maybe cloud base would have been maybe 5,000 feet. And of course, cloud base doesn't come down, but the cloud tops rise up. So the convective layer comes up because the cloud tops are deeper. So maybe 2,000 feet more, 2,000 foot deep cloud. So maybe base at 5, top at 7, something like that. And then no cloud at all. So what was the depth of it? I don't know, 3,000 feet?
Okay. Yeah,
Something like that,
yeah,
3,000 foot amplitude.
Curious.
I feel we get so much of that here. I always look at the day, what is supposedly a thermal day, and we end up with a decision, and we have a discussion. Is this going to be a thermal day, or is this going to be a wave day? And it usually ends up as we get the classic wave days, but we end up with days where we get both.
Yes.
And
yeah,
particularly in northwesterners, and there's always a decision between thermal pilots and wave pilots as to what they're going to concentrate on. And the number of times I'll always go for wave. Well, I'll say I'll always go. I have a good look at the tepograms, at the wind profile and all the rest of it, right? And I'll say, I reckon this is going to be a wave day, and that's what I'm going for. Zed will fly a thermal task.
Well, actually,
Below it.
I'm smiling because I was watching 2 or 3 years ago. It was exactly one of those days, and the tracks in Spot the Gliders. There was you and Alistair going sort of southwest to northeast, and there was Zed and John Galloway who were flying. So you got these tracks just doing that, and then you were about 3,000 or 4,000 feet above them.
Yeah,
it was kind of amusing. I thought, well, okay, there's the thermal pilots going up
Yeah.
and down the wind, up and down some street, well, not streets, but up and down the down the wind, and you were going across the wind in the wave. It was quite funny.
yeah. And who was the faster?
Well, the wave pilot, probably.
Absolutely.
Yeah.
Well, sorry, that's my pet thing, but but no, we get that all the time, and it's a matter of recognizing it.
Right, it's a matter of recognizing it.
Yeah.
That's the point. It's a matter of recognizing it. But this is why I wanted to talk about the mechanism of wave, and I wanted to talk about the way the ridges work in terms of stability and how the wave is generated from the ridges and how you operate at the bottom. Even though, if you've got any sense on a decent wave day, you'll be around here. You still need to understand what's going on for the not decent wave days when it's all mixed up and it's all, they're kind of working against each other. You need to understand what's going on. So I've drawn the shadow of the rotor cumulus. We've tried to make this three-dimensional. The rotor cumulus energy lines are both up and down wind, but in a crosswind patch. And the crosswind patch is a crosswind patch parallel with the generating ridge. And here's the thing about the generating ridge. The intensity of the wave, if you're ridge soaring, you fly the front of the ridge. If you're wave soaring, you fly the back of the ridge upwind of you, because it's the drop off of lifted air. The air's lifted, 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 and the mountain might come down like that, in which case the drop off isn't very severe, or it might come down like that. Those big glaciated, what do you call them up here? Corries?
Glens.
Those big drop-offs that you can have in some places, great trigger for the wave to start up. So the wave mirrors the shape of the back of the hill, nothing to do with the front of the hill. And this is really important as a soaring pilot, because you look at the hill and you look at the wind and you look at the front of the hill automatically. But if you're a wave soaring pilot, you look upwind, you look at the back of the shape of the back of the hills in front of you. Anyway, so here we are. Let's pose a problem. Let's work out what's happening if you try to go from, say, here into the wave. Maybe you come off here and you're going forwards and it's just like, it's fine and there's thermals and thermals. Then it's kind of really, really ragged and broken and more or less blue. And you just can't get a climb, and you get to here and you can get up again and you can get up again. You think, oh, I think it's waving. I think it's waving. So it's like a 6-knot thermal to 4,000 feet. And then everything else is 2 knots of broken rubbish. And then 2 knots of broken rubbish, 2 knots of broken rubbish. 6-knot thermal to 4,000 feet, a wave enhanced thermal. It's in the right place. So let's define the right place. So you can see the overall pattern. What I want to do is zoom in on one of these areas now. Is it getting on your nerves? I'm just walking around it. So, flat ground. Rotocumulus. A little bit of wispy cloud there. Wind. I'll keep doing this. Wind. The highest part, the deepest part of the convective layer is where the temperature profile is the most advantageous for making deep thermals, and where the wind on the ground is quite low. So this is a really good place to find thermals. But the wind is doing this generally, and the wind aloft is stronger, and these come back all the time through this volume. If it's a mountain wave, the characteristic of mountain wave is it stays still, right? That's the point of mountain wave. It stays sitting behind the triggers and it just stays there. And the rotothermals are forming and moving backwards underneath the arch of the wave in this good place for thermals. But each thermal bubble will do this. Let's say a really good thermal starts off from here. As it sucks off the ground, it might even pull the windsock the other way. The wind might even reverse locally. And the thermal starts off here, and this is a good place to be. But where's that thermal going to go? It's going to go here, it's going to go here, and it's going to become that. So at maybe this is 4,000 feet. At maybe 2,000 or 3,000 feet, you'll find yourself climbing in this and drifting backwards. And as the thermal drifts backwards, you come out of the region, which is the best part for making thermals. Now, this will go up and drift back, but think about what's happening when the thermals actually run into the laminar layer on top. You can see I've drawn them as rotothermals. That is, they're leaning back, because of course we know that the wind here is doing this and the wind here is doing that. So I've drawn slightly tilted flow. Underneath the wave, you still feel the oscillations as a very slightly tilted flow in the wind. in some places. No tilt here. But forward, the flow is slightly tilted upwards. Backwards, downwards, downward, the flow is very slightly tilted downwards because, of course, the air's thickening, thinning. So you get a slight upwards flow here, even when you're not in the wave. Even in the thermal layer, the air is oscillating a bit. So a little bit of lift here, a little bit of sink here from the tilted flow. And of course, let's say the tilted flow is giving you +1 here, -1 here. What does that look on the variable? Netto +1, well, the total energy variable goes to, instead of -2 or so, it'll be saying -1, -0.5, -0.5, beep, 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 -0.5. Ooh, there's thermals here. So maybe there's a thermal here. Whereas here, you know, normally at 60 knots, it's -1.5. Now it's -2.5. You speed up a little bit, it's -3.5, -4. And suddenly, oh God, there's really strong sink here. Because the glider goes down all the time through the air, the effect of this tilted flow is asymmetric. 1 knot up and down gives you nearly staying level or going down quite fast. You can see it, if you use Netto, you can see it's just 1 knot up and down. Anyway, tilted flow. So the thermal comes up here and it drifts backwards. These things are getting spun up. And you end up, the thermals coming up here, what there is of them, are still getting spun up. So this whole volume here, the interface between the thermal layer and the wave layer, the laminar flow, is full of vorticity, lots of vorticity. And vorticity in this direction, that's the top of the layer, like that. It's getting spun up like that along the top. This is why when you're flying underneath a good wave system, the nature of the turbulence is very distinctive. If you're flying along and the glider goes, da-dum, like that, like God reached out with a hammer and hit you, you know that feeling, blam, blam. What's happening is you're flying through that. So you get down and up, or up and down. So the glider goes boom, like that, and everything flies up, and the 720 flies up and hits the canopy, and you have everything tied down, don't you? So if you start climbing here, you will end up here because it's a treadmill. You have to go forwards. So let's imagine you take a climb here. Let's imagine you come in here and you go, oh, 3, 4, 5 knots, 4, 3 knots. And then around about here, it goes blam, blam. And you go, oh, push forwards. Blam, blam. Push forwards. Push forwards. That's how you get up in the, underneath the arch of the wave, underneath the rotor Q. You're not too close to this effect here, this blam blam effect, but you are influenced a little bit by that vorticity and by the general acceleration and downflow that you're going to get on the back of this arch in the convective layer. So generally it ain't going to be very good here. So the good place for finding thermals is this volume here. I would say probably this volume here in space. That's a box. It's a two-dimensional box, but of course, there's a box. There's a two-dimensional box, but of course, if the wave trigger is coming out here like this, and the wave bar is like this over the top like this, over the top like this, and you can fly down the wave of the bar here, then this is it's a long box. It's a long volume in the rotor thermals. So you get up here. From here to here, the transition is kind of difficult. It's difficult because as you move forwards here, the thermals get weaker and crappier because they're coming up from an area which is windy and broken, and generally the thermals are not so good. So you need to go forwards with as much height as possible. And once you start flying in this area, you're flying in the bits of the rotor thermals that have been spun up. They are the tops of the rotor thermals because you're flying forwards And when you look forwards, you have to imagine from here, you're looking forwards and you're seeing the convective layer going thinner, 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 thinner. It's coming back towards you, back towards you, back towards you, suddenly seeing little bits of cloud. And those little bits of cloud that are forming are the very, very tippity tip top of thermals. And then they're coming back to you. And you need to get above the tippity tip top of the thermals here. So when you're doing that, you're operating in the volume, which is getting spun up, which is horrible. The place to be, the place to get through, the volume is something like that. There's a bit of a letterbox you have to fly through. If you go through lower than here, you won't contact the wave. And the thermals are not so good out here, and you won't climb up again. You'll climb up back here, but you won't climb up properly here. You might start here and end up here. But if you come down here, you're not going to do it. So you've got to be as high as you possibly can to get yourself forwards through here. And quite often, this is shallower than your raw glide angle in the pure wind. So you have to dolphin through these rotor thermals. You have to make some energy out of the rotor thermals. So that's the first lesson. Look underneath the arc of the wave. There's the volume where you'll get up. You have to keep going forwards because it moves backwards all the time. You have to stay the same distance behind the hill that's generating the wave. You have to get right up as high as you possibly can, right into the wispies and stay in the wispies, and then pushing through the rotor into the wave. You've got to be as high as you possibly can. And this is its own thing. It's coming close and closer again. This is its own thing. You're looking at the very front of the rotor system here. Here, you have pure laminar flow. Here, you have pure thermals. In this area, you have the results of thermal activity. Vorticity, and the wave will do this. The wave will do that. It'll hump up over each thermal mass. This rolling wave phenomenon, this is a shear wave on top of the thermals coming up. Almost always in a wave system, you'll have shear between the thermal layer and the wave above. You'll have a shear system. And above each thermal, the wave will rise up. So you can possibly fly a profile and eventually I've pushed through into the shear in front of this thermal. Now, you could possibly contact the genuine banging wave out in front of all this, but it depends on how steep the slope is.
I mean, the thing, to me, as a sort of summation, you've got the boundary layer where the flow is turbulent. You've got the laminar flow, which is the wave, and you've got that transition layer in between the two, which is the turbulent bit. And the problem is making that transition. And I think, you know, and I'm sure there's plenty of us that have done it. And to me, it's like climbing up a rock face on your using your fingernails. And you spoke about dynamic soaring. And to me, you know, you do exactly that. You've got you move all the way forward and you can see these little wisps and all the rest of it. And you just, every time you get a gust from one of these vortices, I just pull back on the stick. I don't give a shit about, you know, luckily I fly a Discus, which is very a predictable airplane. I have not been able to spin it, you know, primarily because I'm so fat, you know. And what I do is I just use every scrap of vertical energy to get through and break through into the smooth flow.
Yeah.
I mean, that would you agree with that?
Oh, completely and utterly. That's exactly what I was going to say next.
Yeah.
Because normally when you fly cross country in thermals, if you're a racing pilot, this business of dolphining through a thermal is predicated on the idea that you're trying to optimize the speed to the top of the next climb. You're in a glide climb unit, and if you dolphin, you get to the next climb higher, but later. And if you don't dolphin, you get to the bottom of the next climb lower, but sooner. And it's a very fine optimization. Dolphin flying is a very fine optimization. If what you're trying to do is minimize the time it takes you to get from there to there. Very fine optimization. Has very little effect on your cross-country speed in the same way that flying a bit faster than the appropriate glide speed or a bit slower than the appropriate glide speed for the thermal has very little effect on your cross-country speed. But we're not doing that. We're trying to get up. We're flying for height. When you're flying for height, you dolphin like Billy shit. You fly right in the middle of the thermal. You use everything and you pull up. I'll pull up and I'll push it over when the glider's like, and you just fly off it. And whatever I'm flying, whether it's a Pukats or an Ash or an ASW24, just pull up real hard. When you pull up through these things, you're pulling up into wind shear. So look at the direction of the flow. Maybe the flow here right now is 10 knots of velocity in that direction. Maybe the flow right now here is 20 knots of velocity in that direction. You've got an increment of airspeed. And the further you can make the glider travel in this direction, the more the airspeed will increase. So sometimes I've pulled up in conditions of intense shear, and I've sort of pulled up from 80, and instead of going 80, 70, 60, 50, boom, it's gone 80, 70, 65, 65, 65, 60, 50, boom. And you see the pulse of extra speed. You watch the ASI and it just stops falling backwards for a moment. Sometimes I've even been in a situation where you've pulled up and the glider's gone, and you've gone, whoa, as the wind's really increased by 20 knots or so, and you feel a thing just, whoa, almost getting pushed, decelerated. Because of course, as the wind increases, the airspeed increases, the glider tries to decelerate over the ground. And you can feel that sometimes. If you have no shear between here and here, it's more difficult to get into the wave, which is something you were saying about a skew with shear. If you have more shear, it's more easy to get from here to here, although I wouldn't know about the skew with thing. You might see the skew with shear a bit more when the shear is stronger. That might be associated, but not causal. Anyway, this is how you get into the wave if you're trying to get at it from the bottom. You climb in the volume under the center of the arch, or maybe very slightly forwards, constantly moving forwards to stay there. You get right at cloud base, and then in the transition zone, you're dolphining through the rotor thermals. Once you get into here, boom, away it goes. Well, actually, what quite often happens is you find yourself in sort of weak lift, and you sort of move forward and it doesn't really work, and then you're not in the wave, and you look behind you and you see a cloud forming, and you go back to the cloud and you climb on the front of it. And quite often we'll find that we climb here just in front of something that becomes a cumulus, and you can actually climb into the wave. If the wind isn't particularly strong, you can climb into the wave by circling in front of a cumulus that forms and drifts back. And then you find yourself here, and you look forward and there's another cumulus rising up in front of you. And what you're doing as you drift back on this is you're circling on the extra bit of lift that's been pushed up by the rotothermal, and you're using that as a stepping stone to get you into the true wave flow.
Yeah, they're just moving ripples, aren't they?
They're ripples, yes.
They're just ripples moving down with the cloud, and you just ride the ripple if you can.
Ride the ripple downwind, get as much out of it as you can. Think of it as ridge soaring the cloud as it goes off downwind, and then you get a little bit more height and you punch forwards. And that, in the same way as you might do this underneath cloud base, you might well do this above cloud base. You do the same thing, but instead of working underneath the base of nice fat cues underneath the best part of the arch, now you're working on the front of the arch and you're working above the tops of new cues going forwards. And you can do that here. You can do it here above these lumps of blue coming up, because these lumps of blue coming up are still going to have little ripples in front of them. So you can even be in this. I've done this loads. And if you fly on blue days, of course, it's all like that. You just get the same structure. So think back to what we were saying about a thermal package massing in excess of 50,000 tons. You know, you have 50,000 tons of air doing this. The wind's going to blow over it. You can use it. The difference between this and flying a ridge, of course, is that you can be inside this thermal package and outside and inside. You can cut in and cut out and cut in and cut out. And this is where on a vigorous system, you get this crack of really sharply disturbed air, and the glider either falls away or bangs on a lot of airspeed or rolls or pitches quite violently. Generally in wave systems, you get turbulence that makes the glider go up or down very violently, very rapidly. In convergence turbulence, you get turbulence that makes the glider pitch and roll really violently. You get this movement in convergences and this movement in wave as the speed comes on or goes away, or you fly in a vertical rotor. You get a bit of pitching and rolling, but the worst turbulence I've ever been in is not wave. It was convergence turbulence on a cool change. I went up Lake Ohau at about 2,000 feet, all the way up the middle of the lake, just getting hammered by this crazy cool change coming through. And I was trying to stay airborne. And I got halfway up the lake and thought, oh, this is going bad. This is going really bad. And Glidden arrived at Twizel at ground level in rain and low cloud. But I've never been in such a state with trying to control the airplane. It was it was almost unflyable. It wasn't violent. It was just almost uncontrollable. Just pitch and roll. Anyway, so that's getting into the wave. That's how the wave works and getting into the wave. I've gone a little bit quickly through that because I kind of thought I really needed to get a move on. We were running a bit late. Yeah, we're done an hour. I'm just wondering whether what to do after this. Just questions on that so far? Finally, we got somebody on a mic. It's taken a day and a half to get there.
It's mainly one for you, Gian. San, is that what you call forward breaking wave, San, or is that different?
That's
it's different, right?
Yeah. I mean, there's always this, it's a matter of getting through from the boundary layer, and what the boundary layer, as has been mentioned, I've got a mic, it's okay. What the boundary layer is turbulent flow where the air is all mixed up, and you've got thermals being created, or sometimes thermals being created, in that layer, and then you've got and then you've got the, above the boundary layer, you've got the laminar flow. I mean, just to define what the boundary layer is, because there's always, whenever you look at a Met chart, they will always say what the boundary layer is. And basically the boundary layer is everything that is affected by ground turbulence, basically by orographic, and leave wave aside, by orographic features where the air has all been mixed up either through solar heating or through ground features. So that's the boundary layer. And then above it, what you have is what's called the true geostrophic wind, right? Which I won't go into particularly, but that is basically, that's pure wind that is flowing along the isobars, and it's nice and smooth, and it's basically a laminar flow. There's no turbulence in it, usually, unless you've got big Q and so on. And that's, and with wave effectively works in smooth air. Now, what you're doing is you're transitioning from that boundary layer to that laminar flow, and there's that transition point, which G is so elucidated on, you know, and it's a matter of making that transition. Does that explain that to you? You know,
every thermal that comes up is going to punch into the shear.
yeah.
So every thermal that comes up is going to roll. It's going to roll. It's going to roll with the extra speed, and it finishes up just being a rotating lump of air going downwind at the interface between the thermal layer and the boundary layer. The whole interface, the whole of the top of the thermal layer is turbulent, and that turbulence sometimes mixes down. So that gives you that up-down thing. And it's very characteristic. You sometimes see features in the clouds. You'll see hairpin vortices. A hairpin vortex looks like a little duster, looks like a little strand of a willy-willy, a little duster, little stream of condensation. What happens with a hairpin vortex is the cumulus is evaporated by the normal processes, but some of the cumulus, you end up with a vortex where it's spun up, and in the vortex where it's spun up, you don't get the same rate of mixing between the inside and the outside. So you don't get the same rate of evaporation. So you get what looks like you know, the trails jets will leave when they pull G and your little streamer, you get those little streamers, and it looks like that, but it's not caused by condensation in the vortex of the pressure dropping. It's caused by non-mixing. And if you look at the internet, you'll see lots of examples of hairpin vortices. They look like little snakes. I call them snakes. So if you see snakes or hoops at the top of the thermal layer, it's sheary at the top. We should just take a quick break and reconvene in 10 minutes time and do the last part of this before we stop for lunch, yeah? We need to take a pee break. Just give it 10 minutes. We'll start again at 8:30 sharp.